Well, good afternoon, everyone. Thank you for being here. This afternoon, I have the pleasure of introducing the speaker of this afternoon, who is going to defend the work that he completed for his PhD dissertation. Mr. Kelly Aman will talk to us about applications of cubical arrays in the study of finite semifields.
Thank you, Dr. Gornett. Thank you to the committee members and to everybody else sitting back there. Thank you for coming.
And Dr. Cordero, too?
You said Cornett, not Cordero.
Oh my gosh.
Can you practice that? No pass.
Sorry, Dr. Gornett.
You filed a close question. I was going to be thanking all of us.
So Cornett.
But he did say the committee members.
Yes.
Is it okay if we turn off the front light, or does that bother you?
I can do that.
Okay.
I was going to, I said maybe not. I'm not going to show up in the video, but that's okay.
Okay.
But if it's easier for you guys to see.
Is that okay?
We can switch back and forth too, so.
All right. So today I'm going to be talking about finite semifields. And finite semifields get their name because they satisfy all of the axioms for finite fields, except that the multiplication in a semifield is not assumed to be associative or commutative. And so the results I'm going to be presenting today have analogous results in the areas of finite fields, but have not yet been developed in the case of semifields. So I'm going to start with the necessary history and background. Then I'm going to talk about the relationship between semifields and polynomials over finite fields. Then I'll talk about how you can determine the automorphisms of a semifield. And I'll conclude by talking about when it's possible to extend subfields of a finite semifield. And we'll finish up with just some further work that I have in mind and some conjectures. So, history and background. So the first examples of finite semifields were introduced in the early 1900s by Dickson. The main motivation behind semifield research from that point on has been, from a geometric standpoint, due to the fact that finite semifields coordinatize non-Desarguian finite projective planes. And in 1960, Albert proved that isotopic semifields coordinatize isomorphic projective planes. And since that point, many results regarding semifields have been presented up to isotopism rather than up to isomorphism in lieu of this result. I'm not going to talk too much about the geometry today, but I just wanted to let you guys know that there is this geometric motivation, and we will be using isotopisms, but again, not for a geometric sake, but more from an algebraic perspective. And in 1963, Knuth showed how cubical arrays could be used to construct new semifields. And since then, nobody's really expanded upon Knuth's work, but his results are still being used. They were used very recently in 2009 and 2012 by the team of Rua, Cambaro, and Rania to construct all the semifields with 2 to the 6th, 3 to the 5th, or 7 to the 4th elements, and 7 to the 4th elements. So, the formal definition. A finite semifield is a finite set S together with two binary operations, addition and multiplication, such that under addition, S forms a group with an identity element 0. The multiplication is both left and right distributive. There are no zero divisors, and there's a multiplicative identity E that's both left and right. That's both a left and right identity element. So the term semifield has become the standard term for these structures, but it wasn't always. At first they were called non-associative division algebras or non-associative division rings. And that terminology has still stuck around, and it's still there in the literature, although the term semifield has become the more common term for these. So in isotopism, let's say you have two semifields S and S prime, and they have multiplications asterisk and star. So an isotopism between S and S prime is an ordered set of linear functions, f, g, and h, such that h of a times b is equal to f of a times g of b. On the left side, that's multiplication in S. On the right side, multiplication in S prime. So an isotopism is similar to the idea of an isomorphism, but much more general.
Do the functions have to be onto?
Yeah, basically. In this setting, they do.
I guess.
There are So you could theoretically have these for more general structures called ternary rings, and I don't think for the ternary rings they necessarily need to be onto, but I know in the case of semifields they are basically bijective invertible linear transformations. And so as I mentioned before, so an isotopism doesn't really preserve much in the way of algebraic properties. It doesn't preserve commutativity. It doesn't even necessarily preserve the existence of an identity element or a multiplicative identity element. But again, if you use them properly and you do have two isotopic semifields, using the result from Albert, those isotopic semifields formatize isomorphic projective planes. And for the purposes of this talk, the primary concern from an algebraic point of view is that they're useful for classifying semifields, and because they are more useful to the geometric community, it's still worth considering isotopism when you're doing semifield research.
So if you take a field and you want to look at all those,
The isotopes?
oh, yeah.
In the case of a finite field, it's only going to be isotopic to itself.
Oh, really? You can't create new semifields that way?
No.
Oh, okay.
And you can actually prove it, but I don't think I did in my thesis. But yeah, finite fields are always isotopic to themselves, and they are not isotopic to any other semifield.
And so that's the next asked about onto, so I guess I missed that bit. So do the number, if you have two semifields that are isotopic, do they have to, and they're finite, do you have
Yes.
the same number of elements or not?
Yes, they do.
They do, okay.
So what you're saying is the isotopism itself an isomorphism between fields?
Yes, in the case of a field, it is going to, well, yes, it's going to be an isomorphism. It's going to be a messy isomorphism, but it will be an isomorphism.
Okay.
But I mean, is the map H bijective?
Yes,
So it is bijective? Okay.
yes. All of the maps are bijective
Okay.
and invertible because of that. And so if you have an isotopism, let's say from S to S prime, then you can construct easily by inverting all the maps the isotopism from S prime back to S.
Okay.
This is in general or just for finite?
This is, as far as I know, only for finite semifields. I'm not very familiar. I don't know if anybody's really looked at infinite semifields necessarily. And so I'm really not sure what the infinite case would look like. Any other questions? Okay, so I wanted to just give a few examples of semifields real quick to help illustrate a little bit about isotopism and just the structure of semifields. So there are 3 isotopism classes for the semifields with 16 elements. And these are 3 representatives of these isotopism classes. Each of these semifields is very similar in structure. They all consist of elements of the form A plus lambda B, where A and B are in F4, where F4 itself is equal to 0, 1, omega, and omega squared, which is 1 plus omega. The addition is defined in the usual way, so the only thing that distinguishes these 3 semifields is how their product is defined. So if you have A plus lambda B times C plus lambda D, if you define it in this way, you get the finite field of 16 elements. If you define it in this way, you get a semifield Knuth called system V. And if you define it in this way, you get one called system W. And so you can see how similar these products are, especially the 2 semifield products with the product in F16. The key thing that's going to make our multiplication non-associative in these 2 semifields is all of the exponents that appear in this product. So by adding in exponents like saying A squared instead of just A, that helps ensure that your multiplication is non-associative. And so all of the 16 element semifields are going to be isotopic to one of these 3 semifields. And all of them share the property that they can be viewed as a 4-dimensional vector space over F2 with respect to a basis. In this case, I'm using 1 omega lambda omega. In his paper, Knuth proved that...
How can they be a 4-dimensional vector space over F2 if you have 16 elements?
Because it's 2 to the 4th.
You're right. Okay, sorry, stupid question.
It's okay.
2, yeah, right. I was doing it the wrong way.
It's
Sorry.
okay.
It's Monday.
So Knuth proved that in general, every finite semifield is going to have that property. So any finite semifield S is going to have P to the n elements, where P is a prime, n is a positive integer. And in that case, S will be able to be viewed as an n-dimensional vector space over Fp, in which case the addition is going to be your standard vector addition. And by distributivity, the multiplication in this semi-field is going to be determined entirely by the products of elements of a basis. And so for the purposes of this talk, I use this notation, f sub p to the n, where it ends way up top, whenever I have the n up top, that's me trying to emphasize that what we're looking at is being viewed as a vector space, as an n-dimensional vector space over that finite field, fp. And so in any semi-field S, unless we say otherwise, S is going to have p to the n elements, and we're going to use star to denote the multiplication, asterisk to denote the multiplication in S. So let's say you have a basis for S, x equal to x1 through xn. Let that be an ordered basis. So a cubical array is an n by n by n array of scalars defined by this equation. Xi times xj is equal to the sum over k of a ijk x of k. And we're going to call this the cubical array generated by x. Now when we're working with these cubical arrays, rather than viewing them as the three-dimensional set of numbers, and I just appropriated this cube that was on this test. It's going to help me illustrate this. So when we're looking at these cubical arrays, rather than look at them as a three-dimensional set, it's easier to look at the matrices that you can form by fixing a particular index. So for example, if you fix the first index, we'll denote that a I star star, and that's going to give us a matrix M where a ijk is equal to m jk. So that's the algebraic way of talking about it. But there's a more intuitive way of thinking about it where if you fix the first index, it's like you're slicing your cubical array along this axis. And then you're taking the ith slice out and looking at it as a matrix. If you fix the second index, you're slicing your cubical array along this axis and taking out the jth slice. Or if you're fixing the third index, you're slicing it along this axis and taking the kth slice out. And so that's not a very, mathematically rigorous way of talking about it, but it does help when we're talking about properties of cubical arrays. So let's say we had a cubical array A. We say that A is non-singular if for all non-zero vectors V and Fpn, the matrix formed by taking the sum over V sub I, A sub I star star, if that matrix is non-singular for all non-zero vectors V and Fpn, then the cubical array is said to be non-singular. And it's said to be in standard form if A 1 star star is equal to A star 1 star is equal to the identity matrix. So this slice and this slice are both the identity matrix. And
so let me try and picture this a moment. So so V's a vector with n
with n
entries,
coordinates all coming from Fp.
and then you wrote V sub I, so it's the ith entry in V, and you're multiplying that vector by the slice. A sub I, which would give you another vector.
Not just the coordinate of that vector V. So the vector V times that matrix is going to be a scalar times the matrix.
Right, I see. That's giving you a matrix, and you're adding up all those matrices.
Yes,
Oh.
to get a new matrix. And then if that matrix is non-singular,
Right.
and it's non-singular for all choices of non-zero vectors V, then that whole cubical array is said to be non-singular, which is kind of a tricky definition.
Do you know any reason why that's the definition?
It's inductively, Knuth defined it inductively from vectors and matrices. So he said a vector is singular if it's zero. A matrix is singular if a vector times that matrix is the zero vector, right? Or if there exists a non-zero vector such that the vector times the matrix gives you a non-zero vector. And then he generalized it out to arrays of any number of dimensions. So in this case, we're dealing with three-dimensional cubical arrays, but in his work, he was like, well, however many dimensions you want. You basically define it inductively. So like a matrix, so technically in his terminology, a matrix times the cubical array would be non-singular if for all non-singular matrices times that cubical array, it'll give you a non-singular matrix, but this is an equivalent way that he mentions that's more simple than having to define what the matrix product of a matrix and a cubical array is.
Well, I guess what's bothering me about this is the fact that the definition chooses to fix the first thing.
Well, he does
So-
prove that if a cubical array is non-singular and you permute its indices, any permutation of those indices is going to yield another non-singular cubical array.
So no matter which index we choose, it will still
Yes.
satisfy it. I see. So yeah, that's what I was getting at. Okay.
So a similar matrix would still be non-singular? If you conjugate it, so you have a similar matrix?
Yes.
Okay.
And to actually do that though on a cubical array will require an operation we'll get to in
Okay.
a few minutes. All right. And so, yeah, so a non-singular cubical array that's non-singular and in standard form, we'll call that a Knuth cube in honor of this following theorem. And by Knuth, did I advance? Yes, I did. So, Knuth proved that if you have a semifield and you let E denote its multiplicative identity, any basis of that semifield where E is the first element of that basis will generate a Knuth cube. And conversely, if you have a Knuth cube, you can use it to define a semifield product on a formal basis, x1 through xn. And in that case, x1 is going to be your multiplicative identity. And so that allows us to say now, Knuth cubes will define semifields. And so we'll let the set K of S denote all Knuth cubes which will define S. And because these cubical arrays can be used to construct semifields, this allowed mathematicians to actually determine all of the semifields of various sizes. So if your semifield has p to the n elements, all you really have to do is look at all of the n by n by n cubical arrays over fp, which are in standard form. So there's at the most like p to the n cubed of those matrices. So have a computer test every single one of them for non-singularity, and then see what you have. So Kleinfeld used a similar approach. His work predated Knuth's by 3 years, but he used a similar approach to determine all of the 16-element semifields up to isomorphism. In 1963, Walker used a similar approach to determine all of the 32-element semifields up to isotopism. And then finally, much more recently, again from 2009 till about 2012, over the course of those years, Rua, Kambaro, and Rania released papers with all of the semifields of orders, with 2 to the 6th elements, 3 to the 5th, or 7 to the 4th elements. And so these are what Knuth cubes kind of look like. So I already gave you guys those examples of those 3 semifields with those products. So with respect to the basis 1, omega, lambda, lambda, omega, these are the Knuth cubes generated by those bases, by that basis, for each of those 3 semifields. So just looking at them, you can't really tell much about the algebraic properties of a semifield just by glancing at this cubical array. So that was one of the focuses of my research, was to try and figure out, if you have a cubical array, if somebody just gives you one, what can you say about the semifield? All right, so Knuth gave us a very powerful tool, and this gets back to what Dr. Burnett was asking about. So let's say you have a cubical array A, and you have 3 non-singular matrices F, G, and H in GLNP. Well, we can construct a new cubical array B by the actions of F, G, and H on A by this product here, which I'm going to call the triple product. Knuth just denoted it by this in his paper. And while it might not seem very intuitive as to what this is doing, going back to the cube and the slices, so what this triple product is doing is, first it takes your cube and slices it along this axis and multiplies each slice by h. Then it takes that resulting cube, slices it along this axis, and multiplies each slice by g. And then, actually this axis multiplies by g. And then finally takes that result, slices it along this axis, multiplies each of the slices by f. So you can do it by hand without doing this triple summation if you want, just using matrix multiplication. But the reason this is useful is because, let's say you have cubical arrays A and B, and you got linear transformations F, G, and H, with matrix forms F, G, and H, respectively, with respect to some basis X. And if we use A and B to define multiplication on that basis, then we get this relationship that B is equal to FGH inverse transpose times A if and only if these functions H of C, B star D is equal to F of C, A star G of D. And so basically what this is saying is, if you have an isotopism, you can express that isotopism using matrices, and you can apply that directly to a cubical array for your semifield to get a cubical array for the isotopic semifield. So just by strictly looking at cubical arrays, you can look at that isotopism relationship without actually knowing anything about the underlying, say an algebraic definition of your semifield. Okay, so this is not behaving. So one last thing.
You might need to point it at the computer.
Yeah. So one last thing that we can get from cubical arrays is, because semifields are vector spaces, the left or right multiplication by an element of the semifield corresponds to a linear transformation. So if A is an S, you can define linear transformations LA and RA, which correspond to just left or right multiplication by A. If your cubical array A is defined by a basis X, then if bold A is the coordinate vector for A corresponding to that basis, then you can actually get the matrix forms of these linear transformations from the cubical array in a very straightforward fashion. So to get the matrix for left multiplication, you sum up with the coordinates of A with the slices of A that you get from fixing the first index. For right multiplication, you just fix the second index instead. All right, so now we can actually start looking at the results. So with polynomials and semifields, well, because of the lack of associativity in your semifield multiplication, exponential notation is not well defined. X squared is fine, but as soon as you get up to x cubed, it could be x times x squared, or it could be x squared times x. So in order to get around this, a common technique is to define two exponential notations on your semifield. So let's say you've got an element A. If you've got a to the I with a left parenthesis on it, that refers to repeated left multiplication by A. If you have a to the I with a right parenthesis on it, then that's repeated right multiplication by A. And for the purposes of this talk, we're going to focus entirely on left multiplication, just to save time, but analogous results are going to hold in the case of right multiplication. So, for example, if you have a non-zero A and S, then there exists a unique smallest positive integer I, such that the ith left power of A is equal to the multiplicative identity. And we're going to call that ith power the left order of A, and we'll denote it order L of A.
So this was a known result or something you proved?
Something I proved, and anything that doesn't have somebody else's name in parentheses is something I proved, although this particular result is pretty straightforward. But nobody else has called it this yet, and this is going to be important in a second. So,
Sorry, go back a moment.
oh, yep. Am I going too fast?
Right, okay, thank you.
So if we're insisting on left multiplication, a straightforward way of evaluating a polynomial at a semifield element is we're going to insist that when you evaluate the polynomial at that element, the exponents in your polynomial are going to refer to left exponential notation in the semifield. So if our polynomial has this form, c naught plus sum over I x, or c sub I x to the I, then with our semifield element, we're going to say c naught is multiplied by the multiplicative identity, and then the ith power of A is going to be the ith left power of A. Oh, sorry. And if f of A is equal to 0, we're going to call A a left root of f. Now, again, because of the lack of associativity in the semifield multiplication, it becomes a little tricky as to when you can use properties of polynomials to actually, evaluate these polynomials in semifield elements. So let's say you have f, g, and h in fpx, and a in your semifield. Then if f plus g is equal to h, then f of a plus g of a is equal to h of a. That's pretty straightforward due to the distributivity in the semifield. What's much less straightforward is the second result. If f of a is equal to 0 and h is equal to f times g, then h of a is equal to 0 as well. And it might seem straightforward because, hey, f of a is 0, you're multiplying it by g, so of course h is going to be 0. But, again, because of the lack of associativity with semi-field multiplication, what you have to do is, when you evaluate h at a, you have to evaluate it in its expanded form. You can't factor out f or anything like that. So,
Now, you wrote this with f on the left.
yeah. Oh, it doesn't matter.
It
could
doesn't
be-
matter, it's
yeah.
also true if
Yes.
f is on the right.
Yeah. And I think in my thesis, I originally wrote it this way, but then I corrected it so that it says, you know, if f or g of a is equal to 0, then that's true. But these two results allow us to start applying the division algorithm to polynomials evaluated as semi-field elements, which allows us to state, or allows us to prove that for any semi-field element A, there exists a unique monic polynomial of minimal degree such that f of a is equal to 0. And we'll call that the left minimal polynomial of A. And so, if you guys remember the linear transformation for left multiplication by A, LA, so that's a matrix, and matrices have minimal polynomials and characteristic polynomials. So, if A is an S, and F is its left minimal polynomial, and G is the minimal polynomial of LA, then F is going to divide G, and A is also going to be a left root of G. Which means, so I haven't talked too much about the characteristic polynomial, but it will also, F will also divide the characteristic polynomial of LA, and A will be a left root of that polynomial as well. And there is a well-known concept in polynomials over finite fields, which is the order of a polynomial in this polynomial ring. So the order of f is defined to be the smallest integer k, such that f divides x to the k minus 1. And the reason I mention that is because it turns out that the left order of a is equal, if f is the left minimal polynomial of a, the left order of a is equal to the order of f.
Okay, sorry a minute, I need to stare at this. So, maybe I'm being dumb here. Is it what? So, does it always happen that a polynomial f will divide x to the k minus 1?
Yes, in the case of finite fields, in the polynomial ring over a finite field, I should say.
And why is that?
I'd have to go back to finite field theory, but why is that? So you've got, you know, an infinite number of polynomials, right, in FPX, because the degree can be however big you want it to be. I'm pretty sure the reason is that basically, if you've got a polynomial over a finite field, eventually you can multiply that polynomial by enough other polynomials that you'll get to some x to the k minus 1 polynomial. That's me hand waving it, but off the top of my head, I'm pretty sure that's why that is.
So the definition is just over finite fields, that there's
Yes.
nothing new there, right?
Nothing new there. That's an existing.
I think it's actually using the fact that, well, okay, maybe you can answer a different question then. See, I believe I know the answer to the question.
Oh, okay.
What can you tell me about a field when you take out the zero element
That it's going to be a group
under
under
multiplication?
multiplication.
And therefore, what do you know about the elements and the non-zero elements in that?
Oh, that they all have a finite order.
Right, so it's really coming from there.
Yeah. Okay, and that is true, and you're right. And so when you do a quotient ring of the polynomial ring over the finite field by an irreducible polynomial, that's what gives you a field isomorphic to your finite field. So yeah, that makes a lot of sense. Okay. But so then the result though, are we cool with the result? Can I go on?
Oh, let me just read that.
The result's really what's cool about this.
Right. No, I did my homework. I read your thesis yesterday.
Yes, so the nice thing about this is that, yeah, because of this, now we've got this property of the semi-field element that's tied directly to the property of a polynomial in the polynomial ring. So we can use properties of polynomial rings and over finite fields to really look at the properties of this element in our semi-field. And in particular, I'm just going to talk about two types of elements that this will help us discover in our semi-field. The first is what we'll call a left primitive element. So an element A in S is said to be left primitive if for any non-zero B in S, there exists a positive integer I such that the ith left power of A is equal to B. So basically, the left powers of A will generate all your non-zero elements. And using those properties, we can prove that A is going to be a left primitive element if and only if its left minimal polynomial is a primitive polynomial of degree n over that finite field.
So when you talk about f being a primitive polynomial, what does that mean in this context?
It's defined in the sense of polynomial rings over finite fields, and in just finite fields in general. So a primitive polynomial in the finite field sense is a polynomial whose root will be primitive in the extension field defined by that polynomial. And they have properties that they're irreducible, and they have to have certain other properties to satisfy being primitive.
Okay, so for f to be primitive, you said a root, so any root or all of the roots?
All of the roots.
All of the
yes,
roots would need
all
to
of the
be
roots will be there. Yes, and that's how you get your automorphisms of your finite field.
Okay.
And so,
Generator. It's a multiplicative generator.
yes, that would be another way of thinking about it. And so, again, going back to the fact that this polynomial has to divide, that the left minimal polynomial of A has to divide the minimal polynomial of LA, which in turn has to divide the characteristic polynomial of LA. Because these primitive polynomials are irreducible, we can say that A is going to be left primitive if and only if the characteristic polynomial of LA is left primitive. So, as I pointed out, anything that's got somebody else's name on it was already proven by somebody else. In this case, this result was proven in 2009 by Rua, Cambaro, and Rania, and then proven a second way in 2011 by Gao and Shiki. And here, this is a third proof, basically, because this is just a corollary to all of our other results.
Do primitives always exist?
No. There do exist examples. So that's why I specifically didn't ever say there's always a primitive element. And similarly, and this is why it's good to have a good way of finding these elements, right? So in order to find your left primitive element, what you do is take your cubical array, look at the characteristic polynomials of all your left multiplication matrices, see which of those is primitive.
So this would be, if you have a semifield with a primitive element in it, this is analogous to having a cyclic root.
Yeah, sort of. Except it's got to be left primitive. So a left primitive element might not be right primitive, and so
So it's left cyclic.
yes.
Okay, so it'd be like a left cyclic root for such a concept.
Yeah.
Yeah, I was gonna say I don't know if that's a thing, but if it's a thing, then
It
yes.
is now. Because we all call it left.
Yeah.
But so yeah, and so a similar thing. Speaking of cyclic, we say an element A generates a left cyclic basis for the semifield if the left powers of A from 0 to n minus 1 form a basis. And we say the 0 power of A is the multiplicative identity. And much like the primitive elements, there's no proof that such an element exists for every semifield, but there is strong empirical evidence to suggest that this is true.
Now, is a basis for S or is S?
A basis.
Basis.
Right. Because, right, so this is going to be a set of n linearly independent elements, right? So, because we're over fp to the n, so, yeah. So, and again, using the properties of the order, we can show that element A is going to generate a left cyclic basis if and only if the characteristic polynomial of LA is irreducible. It's going to make sure it's of degree n, and since it's going to be irreducible, your lower powers are going to be linearly independent. And a corollary to that is just that every left primitive element will therefore define a left cyclic basis. And so, again, like I was saying, basically if you get a cubical array, you can look at all the matrices, and you can at least see whether or not you could generate a left cyclic basis or whether or not you have left primitive elements. And that's...
So are you saying, you said there's strong evidence, blah, 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 right?
Yeah.
So are you saying there is no known example of a finite semifield that does not have a
Yes.
left cyclic basis?
Or, I'm not sure if I should say specifically left cyclic, but I know there exists at least a cyclic basis, either left or right, for every known example of every known semifield. So nobody's found a semifield where it did not have either a left or right cyclic basis.
Okay.
Can it have a left one without having a right one?
I'm not sure. Maybe. I'm kind of weird in insisting on looking at left multiplication. Most people look at right multiplication. It's just how they do it. So that's why I feel a little hesitant to say some things, because I know a lot of this stuff is true in the case of right cyclic basis, but I don't know necessarily for a left cyclic basis. But again, and yeah, like I said, there's strong evidence to support this, though. The idea that one of these always exists.
Isn't there like a kind of a natural thing where, I mean, I know for rings, there's something called an opposite ring where you just define the multiplication in the other order. Did they do the same thing for?
Yeah, that's called, in the case of semifields, that's called the dual of the semifield. And that's because they coordinatize, so they coordinatize projective planes, so the dual semifield coordinatizes the dual plane of the projective plane from that first semifield. But the definition is just by reversing the thing. Those might not be isotopic, though, even. So because they might not be isotopic, they might not be isomorphic, and so we can't say for sure. But if there is one with a left cyclic basis, then there's going to be one that may be isomorphic to it that will have a right cyclic basis.
So the dual one will have a right cyclic.
Yes, if the first one has a left. Okay. So, and the reason I point out this left cyclic basis and the primitive elements too, those are going to actually help us when we're talking about finding the automorphisms of a semifield. How do I do it for time, by the way? Okay. So, we started a little late. Do you guys want me to, should I rush through the rest of this, or do you want me to take my time?
I'm enjoying it.
Okay. Okay. The rest of y'all, if y'all have to leave, don't feel bad. Okay, so I am going to take my time with it. So, in order to determine the automorphisms of S, it's going to help to really understand what K of S look like, the set of all cubical arrays, the set of all Knuth cubes which define S. And to help us do that, we're going to kind of standardize our definition. So, in Knuth's theorem, he says you can use a Knuth cube to define a semifield over a formal basis,